parallel implementation of digital filter or realization of a digital filter is shown in this example for this transfer function h of z. By parallel, I mean input samples are coming in. As you can see, they go in parallel into two second-order realization. These are second order because there are two registered there, and they are in the canonic second-order form. So you can see that they are in parallel, and then the output of these separate second-order system are coming out in the form of samples, and then these two outcomes or output samples are added together to form the final output sample. So this is the meaning of parallel implementation. Now, how do we do this? How can we come up with the value of, say, coefficients b0, b1, b2, a1, a2, and also the other 5 coefficients? So each of these second order system, they have 5 coefficients. To do so, I need to be able to rewrite this h of z in the form of, say, z to the 2 plus some coefficient z plus some other coefficient, and then do the corresponding numerator polynomial, and repeat that as well. Another second order, given that the denominator is fourth order, I expect to have another second order with some coefficient times z and another coefficient and another numerator. So I need to be able to rewrite h of z in this format. That's my target. Okay, so to do that in a standard fashion, by the way, I'm going to switch to Matlab very soon to show the shortcut to do this process rather than tedious manual calculation. So just bear in mind that if you want to do so, you need to do the partial fraction expansion of the h of z, partial fraction expansion, and by that, or basically PFE, and by that, what I mean is you need to find the roots of h of z and find the partial fraction expansion. But while that is doable, it will be tedious. So instead of doing that, what I'm going to do is I'm going to use Matlab, which has a very good function for this purpose. So let me switch to Matlab, and that function is this one. So I'm going to use residuez. So just to show you what I mean, this function residuez, which I click for help, you can see that residuez is, so this function is a z transform partial fraction expansion effectively for you. So what it needs at input is the coefficients of numerator in the h of z and coefficients of denominator in the form of two row vectors, and then it would give you, if you use this function in this format, it will give you 3 outputs or 3 arguments. R will be the numerator polynomials or coefficients for your partial fraction expanded h of z. This is the h of z here on the left hand side, equal to the partial fraction expansion results. So you will have poles in the form of p1 times z minus 1, p2, z minus 2, and so on and so forth. And you will have r1 constant up to rn, and then you will have some, potentially, not always, some polynomial like this. In this case, we won't have this portion because the order of numerator is, well, in z minus 1 is less than denominator. So you're supposed to find this k, by k I mean this whole thing, and then p, which will be a vector that contains p1, p2 up to pn, and then r, which will be another vector that contains r1 up to rn. So we need to find them. Okay, just a heads up that this function, interestingly, can be used the other way as well. If you have rpk, you can feed it, and then it will give you back the numerator-denominator coefficients. So let me use it. I'm going to use it exactly as it said. So let me clean. So maybe that's easier. Okay, so I am going to use it exactly as was instructed. All right, so I am using the residuez, and then as you can see, let me switch back so that you can see it easily. These are, so take a look at the coefficients in numerator: 14, 2.7, negative 3.66, and 1.135. You can see that those 4 coefficients are already here. I have them: 14, 2.7, negative 3.66, and 1.135. And also 1.5 negative 0.39, and 0.005 and 0.1 are the coefficients from denominator. If I switch back, you can see it. There you go. 1, 0.5, negative 0.39, and 0.005 and 0.1. So these are just copy pasted, and if I run this, there you go. So you can see that. Let me just switch to Matlab so that you can see it. So I just ran it, and then you can see it reports back residues of these values, which are effectively, there is no imaginary part, all pure real, 3, 2, 2, 7. And these residues correspond to poles that are shown here. Minus 0.8, a pair of complex conjugate poles, 0.4 plus 0.3j, and 0.4 minus 0.3j, and then 0.5 real. And then k is nothing. The empty means there is no k polynomial. Okay, so let me rewrite this. So I'm going to copy paste these values. So what I did, I ran this function. If I copy paste it back to, say, okay, if I copy paste this here, I'm going to keep it for reference. Okay, so these are what I copy pasted. Let me just make sure that you can see it. Okay, so these are the residues, and let me remove this portion. These are the residues I found, and basically all these residues are just real numbers. I don't need fancy things, so let me just write it this way. That's easier. So the residue I found, residues are 3, as you can see here, copy pasted from Matlab, 2, 2, and then 7. Let's make it simple. And the poles I found are a little bit more busy. So poles are, okay, poles are, as you can see, I have minus 0.8, and then I have 0.4, and then plus j.3, that's the complex number, and I have 0.4 minus 0.3, or minus j.3, and then I have what? I have minus 0.5. Order matters, by the way. Be careful about order, because these poles are corresponding to those residues you see on top. So minus 0.8 correspond to 3, and these two guys correspond to these two guys, and then negative 0.5 correspond to 7. So what is the use case of these things? Very simple. So we are doing partial fraction expansion using, effectively, as I said, using residue z command or function in Matlab. So I'm going to just remove this. What I did effectively is this one. So multiply both numerator and denominator in this whole thing by, so multiply the whole numerator and denominator by, say, z minus 4. So you get h of z equal to 14 plus 2.7 z minus 1 minus 3.66 z minus 2 plus 1.135 z minus 3. So that's what you get in numerator. So numerator is a polynomial of order 3 in terms of z minus 1. And then you have 1 plus 0.5 z minus 1 minus 0.39 z minus 2 and plus 0.005 z minus 3, and finally plus 0.1 z minus 4. Okay, so that is what we can write in z minus format. Now, what is the next step? The next step is use what you found in terms of residues and pole and rewrite this whole thing. So I am going to do so exactly. So what do I have? I have equal to. Okay, how can I use this 3 and the negative 0.8? That is effectively like this. So you have, what you have is in this format. So in your, for numerator, you have 3, because that's the 3, and for negative 0.8, you have 1 plus Because what is that meaning, the negative 0.8? It translates like this. You will have, effectively what it says is, you would have 1 plus 0.8 z minus 1. So that's how you write it when you want to use it. And what else? Because the meaning of this is you're saying z equal to 0.8. So if z equal to 0.8, then z equal to negative 0.8. That's the meaning of this, just to make sure that you guys understand what is the meaning of this. So z equal to negative 0.8, that means 1 plus 0.8 z minus 1 is 0. So that is what you have as your denominator, and that's exactly what I wrote. So just wanted to clarify. Okay, what is the next? So you have a plus. The next is, let's say, 7 and minus 0.5. So you keep 7, and then 1 plus 0.5 z minus 1 plus. And you have a 2 for now. You have a 2 for here and corresponding to this guy. So you can write 2 and 1 minus 0.4 plus j 0.3 z minus 1 plus another 2, 1 minus, this time you have 0.4 minus j 0.3 z minus 1. Okay, so this is the partial fraction expansion of the h of z utilizing the residue z function in Matlab. So now we can combine these because we don't want first order systems, and by the way, there are complex coefficients. We don't want them. We want real coefficients because the original system is a system with real coefficients. Okay, so let's combine them now. So I'm going to use a different color so that I give you a contrast here. So it's equal to, when you combine these two together to form a denominator that has a second order polynomial, you will end up with 1 plus 1.3 z minus 1 plus 0.4 z minus 2. And of course, when you finish the arithmetic, then you will end up with in numerator 10 plus 7.1 z minus 1. That's for combination of these two guys. Now, we can combine these two naturally because the poles are the complex conjugate poles. So if you combine them, we get rid of the complex coefficients. So you end up with, if you combine them, the denominator becomes 1 minus 0.8 z minus 1 and plus 0.25 z minus 2. Okay, and numerator becomes 2 minus 0.8 z minus 1. You're done. So what we did here effectively is we managed to form h of z that was given as original transfer function in the form of a sum of two transfer functions that are second order system, as you can see, because the maximum order observed is the second order. So now we can use these two transfer function can be realized using the structure that is given here. Let's say, for example, you are going to use the first structure. So let me use a different color to highlight. Let's say this structure to realize this guy. Okay, if you want to do that, then you will see that obviously you have a 10. So since you have a 10, you will set this b0 to 10, and then you see that you have a 7.1, so you set this one to 7.1 for b1, and then there is no z minus 2 in numerator, so b2 is 0. Now you can see that in denominator you have 1, so matching what is expected, it should be 1. Okay, and then you have this guy 1.3 z minus 1. So we need to be careful about that because this, whatever you see here, you have to negate it to implement for a1. So a1 will be minus 1.3, not plus 1.3. Remember that when you are implementing a transfer function like this, whatever coefficient in denominator should be negated when you go back and put it into this direct canonic structure. Canonic meaning that it is implemented with minimum number of registers, in this case or second order system, hence 2 registers minimum that is possible. And A2 is negative 0.4 because we have a plus 0.4 z minus 2 in denominator, so A2 is negative 0.4. Okay, great. So we found the 5 coefficients in the top structure, top second order structure. Now for the bottom second order, this one here, we're going to use it to realize the second transfer function here. So let's do that. Same. So we have a 2, so you put 2 here. Then we have, maybe I use a different color so that it's observable. So you have a 2 because of this 2. Okay. And you have a negative 0.8, so you have to use negative 0.8 for the next one. And then there is no z minus 2 in denominator, in numerator, so therefore we have to set this one to 0. And again, it's very important that we have 1 in denominator because that matches with the format we have here in terms of a wire. So this is a wire, which indicate that we should have a proper 1 there. Now we have negative 0.8, which will become plus 0.8 here, so 0.8. And then we have plus 0.25 z minus 2, so it becomes negative 0.25 for this last coefficient. All right, so as you can see, using just partial fraction expansion realized by utilizing Matlab's residuez function, then properly translate the reported values of residue and pole back to parallel structure, then we managed to find the proper second order systems that are added together to realize h of z given to us, and then use the found coefficient to program the parameters of the parallel structure as discussed in this example. I hope that this is helpful.